Good morning. I am Krishna from Krishna's classroom. We begin with another episode of diagonalization. Last time we discussed certain interesting results, namely when D is diagonalizable, what happens to Ft? And we found that when F is the characteristic polynomial, then Ft equal to 0. We also saw another result. I defined a function g from related to F. Of course, g divides F. And all the linear factors that occur in F are there in G with the exponent 1. And for such a G, Gt is equal to 0. I mean, all these have been proved by falling back on the fact that T is diagonalizable. The proof heavily depends on that. However, I made a comment that the characteristic polynomial annihilates T. I have not used this terminology earlier, but we will do it soon. In the sense that f of t equals to 0, whereas g of t may not be 0 in the general case. Now, this is the sort of results that we looked at last. Now, I found that while discussing this with some of my friends, probably, I think there is some kind of a clarity problem somewhere. If I thought that, I think in the last lecture I had used the matrix representations of the diagonalizable operators in a way to prove certain results. So, let me just recap some of the things that I did earlier. In fact, I have done it, we emphasized it very much in the earlier lectures also. But this is one problem. This is the central problem is given T belonging to LV, we have to get the space reworked such that T is very transparent, in the sense that we have to devise a suitable ordered basis for V related to T such that T looks very transparent. Something like this, the ordered basis should span certain invariant subspaces, so that T confined to the invariant subspace will ignore what is happening elsewhere. So you get a much better view of T. As you know, if you have a linear transformation which has the property that it maps, or it's the action on the ordered basis is that it just scalar multiplies each of the vectors. In that case, what happens? You know that the subspace spanned by these vectors are linearly are invariant under T. So you get a much better view of T. Whereas if you take just the standard basis and start working on it, it has nothing to do with the T. And the T may appear to be very complicated. And little bit of transparency can be brought in by possibly choosing an appropriate breakup of V into invariant subspaces of T. Now this is our task primarily. And initially we are looking at a class of operators which are diagonalizable. We defined it. Now we are working on that. But as I said, how these matrix representations can be made use of improving certain results. Let me go back to our diagram. So you have map from B to B. T is a linear transformation. B to D. Now what you have seen is that if you introduce an ordered basis for B, this will take you to F n cross 1 to some column vectors in F n cross 1. And if you want, you can call that by this map is phi, which is subordinate to G. Similarly, you have the map to n cross 1. This is again phi, which is subordinate to the ordered basis B that you choose. Then we have seen that corresponding to the linear transformation T carrying V to TV, the image of V, which let us designate by X, and this I can designate by, you have an n by n matrix A, which takes it to AX. Now A is essentially the matrix representation of T relative to the ordered basis T. Okay, so you can transfer the whole activity from V to F n cross 1, which is far more familiar to you. And once again, the rather than dealing with an abstract operator T, one can deal with an n by n matrix. That's the advantage. And we also saw that there are several possible representations from which you can possibly choose a very convenient one. These are all the advantages. But that is not the point that I want to make. What I want to make is that properties of T can be studied using the properties of A. For example, if you take A to be, if it so happens that the ordered basis B is such that A is diagonal, something like lambda 1, lambda n. Some of them may be repeating. Okay? Then what you have is that you observe that A of EI, where EI is the column matrix corresponding to the column matrix delta ij. Now I will just write it down. This is equal to lambda I. So EI is essentially column matrix. Now one observes that, see, if EI is an eigenvector of A, then phi inverse EI is an eigenvector and lambda is the corresponding eigenvalue of this. We have already seen it. It's very easy to see because you know that after all, what is A? A is essentially phi inverse that is the relation between A and T. Phi is an isomorphism. Phi is an isomorphism. It's a linear isomorphism of V to F. So that is something that we already know, and therefore, because it's an isomorphism, whatever is happening in V, the same thing is happening with Fn plus 1 carried through the map phi. Now this is the advantage that you have. So the behavior of A will be essentially telling you how T is behaving. For instance, if you take any subspace of Fn invariant under has a counterpart in V, which is left invariant, which is invariant, this is what is happening with the eigenvectors. You have the eigenvector here, so you pull it back into V. It turns out to be an eigenvector of T. Eigenvalues of A are the same as the eigenvalues of T, and more generally, any subspace of Fn cross 1 invariant under A has a counterpart in V, which is invariant under T. Now, that is if M is a subspace of A of M, then phi inverse of M is a subspace of V and T of this is quite easy to do. So what I wanted to say, I mean, this result has the advantage that in proving theorems on T, you can go to their counterparts statements on Fn cross 1 and try to prove the theorem there, and then translate that proof back to proving results on T. It is advantageous because here we are working with matrices. Here it's an abstract operator. So there is more visibility here. You can compute easily because the entire knowledge of matrix operations is in your hand. You can make use of them and you can try to make observations using those computations. And all those observations do have a counterpart here, and that's the advantage that you have. So you can use that. In fact, you recall last time I think I used this in the proof of a result. That is, see, you had this talking about working about this P minus lambda I. And then we said that the null space of this was denoted by Wi. Okay? And we were looking at the structure of Wi. Okay? Now this is essentially spanned by the eigenvectors of T. Correspondingly, what you have is this. You have the picture, the null space of, because T is diagonalizable, this is diagonal, this is I itself, this is the identity matrix. Now this is equal to a certain MIC. So if the null space of this operator is Mi, then Wi is equal to phi inverse of Mi. Okay. So once you get it's easy to get the null space of this. This is quite simple. Okay. Right? Especially suppose then it is of the form something like this. Then A is equal to some lambda 1, it's a block. Then you have lambda 2, lambda k. So lambda 1, lambda 2, lambda k are the distinct eigenvalues. A as well as T. So the matrix takes this form into blocks. Now this one is a d1 by d1. How many times lambda 1 repeats? And this is dk block, and this is d2 cross d2. Okay, and in that case we have also seen that f lambda is the characteristic polynomial and you have d1 plus all these are available, straight away available. Okay. Now what you can see is that, see the space spanned by, see, corresponding to lambda 1 there is a null space. See, there is a null space of t minus, so we have got mi. What is mi? Mi is spanned by, see, according to our notation, it will be a certain EIs that span the whole thing. Some of the EJs whose span is equal to this. Pull back. When you pull back those the unit vectors, you get certain vectors here. The corresponding vectors will span a certain subspace, and that subspace is essentially the same as the subspace, the one that corresponds to this, and that's your Wi. Okay, and that is obtained by this. So quite often you have the advantage that if you work with the matrices, the results over there for matrices can be judiciously looked at and pulled back, and then you get the corresponding counterparts of those results, and they are readily available to you. So the powerful way in which you can approach T is by going for the most simple representation for T that you can make. I mean, this is what I said. You are seeking a representation which is most simple in the sense that it should be easy for computation, which means that a lot of zeros should appear in the matrix. It should have certain structure which is easily amenable for what is called, especially multiplication in the computations. The second part is it should be visible. So here there is a lot of visibility that every eigenvalue, or sorry, every eigenvector is left invariant by A. So correspondingly, phi inverse of the eigenvectors which are EIs, they are left invariant by T. Now this is the advantage, great advantage that you have. Okay. More generally, if you have any subspace here which is left invariant by A, there is a corresponding subspace left invariant by. Now this remark I wanted to make, and I think that enables you to carry through the computations very easily. So that's just it. Now we go back to the diagonalization problem. Now you recall the results that we did on general projection operator. We defined what the projection is. And projection has two parts. One, we say projection onto something and projection along something. Secondly, you can easily recognize a projection operator because it is an idempotent. Every idempotent operator is a projection on its range space along the null space. Now this is the theorem that we proved last time. So we are going to exploit that. Okay. So throughout this discussion, we will keep this condition. Or it basically we say that P is diagonalizable. Assume. This is assumption. Therefore, it has a matrix representation which is diagonal, and you have already explored what it is all about. Essentially, what you are doing is, for the vector space B, we choose these eigenvectors as the ordered basis, and with respect to this ordered basis, T has a diagonal representation. That's what you mean by T. In short, it says that such vectors do exist. Okay, when we say T is diagonalizable, there exists eigenvectors of T with the property that they form an ordered basis for the vector space, and consequently you have the matrix representation which is diagonal, and the elements that appear along the diagonal are nothing but the eigenvalues. So this is what we have to see. Right. So now we start looking at this structure. So let me define. We define Wi to be null space of T minus lambda I. First, lambda i's are the and what you have is, in this case we are assuming f lambda, this is a characteristic polynomial, equal to nth dimension of theta. This result we have. I mean, this is what we are assuming. When we say that T is diagonalizable, all these are assumed. One thing that you observe is that Wi's are the eigenspaces T associated with the eigenvalue now we assume lambda I is different from lambda whenever I is different from these are the distinct eigenvalues. And the multiplicity of each of these eigenvalues is d1, d2, etc. dk. And we also found that dimension of, in the diagonalizable case, dimension of Wi equal to di. And this is something which cannot be assured in all cases. Only in the diagonalizable case we can measure this. More generally, what you have is 1 less than or equal to dimension of WI less than or equal to 0. This is the more general result that you get out of this. Sometimes it fails to meet this number. In that case, T becomes non-diagonalizing because we will not get enough eigenvectors to span the whole vector space. And we also have this result. We have proved that Wi intersection zero vector, and our I is different from. Because here I becoming, in all these cases we are having I 1 less than or equal to I less than or equal to K. Now let me work on the further structure of this. And we have also proved the following. Under these circumstances, V can be resolved into the sum of W1, W2, etc. Under these circumstances, we can write namely that T is diagonal. Diagonalizable. We have V equal to WK and WI and we also have dimension of of our discussion, the results from our discussion on what are called the projection operators. Okay, so let us discuss. Now let me define certain linear transformations on V called the projections, as we explained in the episode of number 28, where we extensively looked at projection operators. Okay. Define how do we define that? You take a V, note that V equal to uniquely different. In fact, this is quite easy, as we have explained this earlier. The Wi intersection Wj equal to 0 consists of only the 0 vector, means that this breakup is a unique breakup for V. Okay, this is a consequence of zero. Whenever I is equal to 1. So we have two things now. V is W1 plus W2 plus etc. Wk, which tells that there exists a breakup like this, and because of this condition, it is a unique breakup. Therefore, now let me define Vi from V to Wi by Pi of V. This is the condition. So we have got I mappings from V to defined from V to V. Okay, and the range of each of these mappings, that the range of Pi turns out to be just Wi. Therefore, there are K mappings defined from K mappings defined, say P1, P2, etc. Pn defined from V to V. Okay. Now the question that you ask is, what is the nature of this map? Is this also a linear transformation? Okay. So what one can prove very easily without any difficulty is that, note that each Pi belongs to LV. It's a linear transformation on V. That's quite easy to do. You take two vectors U and V, and then go for their breakup, go for the definition of, and compute what is Pi V plus U, and see whether it is Pi of V plus U equal to Pi V plus Pi V. Similarly, Pi of CV equal to C times Pi V. I mean, these are very easy to work out. Therefore, they are not just ordinary mappings, well-defined mappings, but they are also linear transformations. Okay. We also observe that Pi square Pi. That's quite easy, because what happens is, this is because Pi of V equal to Wi, Pi of which is equal to Pi. Therefore, Pi square equal to Pi. Okay. That is pi square equal to pi. This is true for I. So these are all idempotent linear transformations, and therefore they are projections. So each pi is a projection onto wi, okay, along wi tilde. Let me define this. Okay, so observe that. So each pi that means you just omit wi from here. Okay. In fact, what you can easily prove is that the null space of pi as a null space of wi. That's quite easy to prove because it follows from, see, you observe that pi follows from that. Pi pj equal to 0 whenever I is different from j. Therefore, the null space, this is this, the range space of pi so what you are doing is you are writing V as this means wi intersection, that is okay. So that is true of every pi. So now what you have is there are k projection operators p1, p2, etc. pk. So now let us see what happens. So given V equal to and this by our definition, what is this is equal to V1 V plus V2 V pk. That I can write as this is true for every V phenomenon. But V is equal to the identity map acting over Therefore, what do you get? The consequence is that IV equal to P1 plus now this is the resolution of the identity. So this is what you call the resolution of the as a sum of projections subordinate to the diagonalization of so we have T given, we are assuming T is diagonalizable. Look at the diagonalization of T. We have the eigenvalues lambda 1, lambda 2, etc., lambda k. The corresponding eigenspaces are Wy, W1, W2, etc., Wk. And we found that V can be written as the direct sum of W1, W2, etc., Wk. Right? And the null space of, so we can define what are called the projection operators Pi onto Wi, which is the range space of Pi, and along the null space of Pi, which is we have designated by Wi tilde. Okay, so we have defined everything. So we have got the resolution of the identity. So identity gets written in this case as a sum of certain projection operators. Now you see projection operators are easy to understand because they play on a subspace, not on the whole space. I mean, they work on the whole space, and but with one shot you get into Wi, then any further operation with Pi, you are always there. They leave Wi invariant. These are the invariants of spaces that you have associated with the diagonalization. Okay, now what happens to T? See, we have again V resolved uniquely as this is unique. Now let us compute TV. What is TV? TV is by linearity, it is PW1 W. But what about Wi's? Wi's are all eigenvectors of T associated with the eigenvalue lambda I. So what we have is this result. Make use of that. Therefore, this is equal to what is that? That's equal to lambda 1 P1 V that's equal to and this is true for everything. Therefore, what do you have? Therefore, P is or T is now expressed as a linear combination of P1, P2, etc. P2 with the coefficients given by the eigen values. Which are the eigen values of that's a very beautiful scenario that you have. You have corresponding to for a given T, you can resolve it if it is diagonalizable into a linear combination of certain projection operators. Not only that, the identity operator can be resolved accordingly. That means exactly what you are doing is you are choosing a coordinate system which is convenient to you, and once you sit in that frame, you have a much better visual perception of what P does. Okay, that's what you have because you are using the eigenvectors to give you the basis. That means provide you with the coordinate system. And once you use that coordinate system in which you see that T stays within the space spanned by the coordinate vectors and it doesn't spill over. Okay? So you have a much better visibility of the operator or what exactly is doing. Essentially, you have successfully resolved this into a very simple class of operators. As the sum of the identity has been written as the sum of a set of projection operators, and consequently the operator T itself is written as a linear combination of these projection operators. Now this is the spectral theorem, and this is exactly what we want. So this is the spectral theorem. Therefore, we have proved the following. So, let me state the theorem. Let the diagonalizer. Let be the distinct eigenvalues of T. With the multiplicities respectively. Let V equal to okay. And you have dimension of V equal to dimension of W1, dimension of W2 plus etc. dimension of W3. This is equal to further now we can define now define And we have that is PIs are projections onto also have so these are in a way orthogonal projection. I have not introduced that term before. In some way it is called orthogonal projections. But let me not record it. We are not said anything about orthogonality. Okay. Right. So in short, this is what you have. EI is the problem. Okay. Further, what you have? Then the identity operator on E as and T can be resolved as into a linear combination Yes with coefficients lambda n the eigenvalues of T. That is this is the so that is the structural side of the whole thing. Now, in the next lecture, what I intend doing is to take up a specific example and then compute everything. The computation is not very simple in the sense that it is laborious, we cannot do. But certainly it would be nice to see how all these computations go, because general theory is very simple to work with. Very nice theorems can be proved. But we would convince ourselves by working on a good example and compute in those cases the projection operators, and then verify that identity is the resolution of those projection operators, the sum of those projection operators, and T can be written. T turns out to be the linear combination of the corresponding projections. Okay, now this is the consequence of diagonalization. Thank you very much.